Today is again last day of November. Time really goes fast. So which means this semester has only 2 weeks left, right? 2 weeks, right? 14. I thought 14 14 is the last day, no, but 13. But I want to do last day of the lecture as a Friday, if you all has no problem. So that's what I intend to do. Then, as I mentioned, quick exam gonna be on following Monday, 10 o'clock in the morning would be good. Okay, I spent some time in chapter 1 and chapter 2, and this is last part, almost the last part of the chapter 2. Chapter 2, if you look at carefully, it contains very important things for underwater explosions. And as you, anybody has a pointer? I forgot. No pointer? 포인터 있어? 그래, 하나만 빌려와. Higyu is not here today, so Higyu usually set it up. So I'm spoiled. Everything is here. It was very good. But today I lost all 3 of them up in Seoul. This equation said that equation is the most important to show the relation between the shock wave pressure and the fluid particle velocity. Fluid particle velocity, you can use fluid. 누구한테 빌렸어? 내가 이따 갖다 줄게. 가다가? 응? 괜찮아? 네. 지금 살아났어? 얼굴 보니까 살아났네. This equation said whether it is valid for plane wave and also the spherical wave. It really doesn't matter. For the plane wave, the second term drops off. Why? Why is the second term drops off? Abdullah.
There is R.
To be qualified to be a plane wave, the R curvature has to be really flat, which means R has to be large and large. So when the R goes to large, 1 over large quantity, then near 0. So you can just delete the second term. So for the plane wave, you have that terms only. U minus U naught is equal to 1 over rho C, P minus P naught, right? For the spherical wave, curvature come into play important role. So this term, sometimes called afterflow term or surge, S-U-R-G-E, the surge term. 영균 받았어? 노트? 네. The surge term doesn't make any difference, which is, if you look at this carefully here, is inversely proportional to R but also function of integration from initial time to the current time of the shock pressure P here. So history of the shock pressure. So as I mentioned the other day, this could be sometimes 10% or sometimes more than 10% to the total. So you cannot neglect this term for the spherical wave problems, okay? So if you look at the spherical wave here, so this is a spherical shock wave front as moving in the radial direction. In front of the shock wave, everything is all calm, very nice. Then bang, which means it's really explosion occurs and the shock wave propagate. U naught, you can set usually equal to 0. I talked about this last Wednesday. Oh, welcome, Yesu. And the P naught is something like hydrostatic pressure in that depth. Yesu, you got the copy of the book? 아니, 있어? And P naught is hydrostatic pressure, and U and P is as usual. U is the fluid particle velocity behind the spherical shock wave front, and P is shock wave pressure. P minus P naught, you can say that is dynamic pressure or gauge pressure. You put the pressure gauge into the water up to the depth you are considering. Then look at the instrument. You can just turn the knob, set equal to 0, get rid of this P naught. Then after that, when you measured in the explosion testing, the measured quantity is what the dynamic pressure is, okay? So any question? Then I'm going to leave this area and we'll come back afterwards. The last topics in 2.4 is reflection of acoustic wave or shock wave, you can say that. And the reflection, if it's just the seabed or bottom of the sea, and the water, if you consider that, not much in it. But always problem occurs when you have air. So when you have air-water interface, that usually generate lots of problem. So this is, then explosion could occur here, and surface ship is right here. Then that's a problem. In U.S., even when you're dealing with the surface ship, for the prediction, or you can say a simulation, well, 2D simulation we started around the mid-1990. And the computing capability is getting better and better. And the late 1990, and we're slowly getting into the simulation of underwater shock problem for 3D. And after that, 2000, 3D simulation was very, very possible. But before it wasn't. dealing with the cross section of the surface ship, so it wasn't good. So this 3D problem and this air-fluid interface problem, a lot of problem exists there. So this section, reflection of acoustic wave, well, I'm going to show you really air-water interface. Before getting into air-water interface problem, I'm going to show you a simpler problem set, which is rigid. Rigid is easy. Then explosion occurs. What happens? If I rewrite this guy, this is a water. Rigid. And I can say this is a water. And this is rigid. The free surface is way up there, like a submarine problem. Okay, it's in the deep in the water. If you come up to the free surface, the life of the boat is ended. It doesn't matter whether it's alive or not, it's same as dead. Once detected, that's a dead. No reason to say still survived. So over here, for the reflection of acoustic wave or shock wave, first you can consider the boundary. For the boundary, of course, you are talking about two different media, surface of the sea or bottom of the sea or underwater obstacles. What can you think of underwater obstacles? Underwater mountain. You know, when we visualize the underwater, you know, we always think, oh, it's a flat bottoms, lots of tropical fishes running around. But not true. If you look at the East Oceans or West Ocean here, Donghae or Seohae, if you go down there, is very severe underwater mountain existed there. Right, Gaulgi, you were in ocean, the research institute, and when you have lots of mountain, situation for detection of the target is very difficult because lots of mountain in the water implies tremendous noise exists in the water. Then try to detect the target, which means submarine, for example, difficult. But blue ocean is much easier. Blue ocean, you can think as a bottomless ocean. Then detection-wise, much easier than such a mountainous the sea, like surrounding the Korea. One of the assumptions for the underwater shock problem, to simplify it, this is very realistic, and the motion of the water or gaseous product is described sufficiently well without introducing the viscosity or other dissipation mechanism if you have it. In other words, for the underwater, to solve underwater shock problem, you don't have to consider the fluid viscosity. Without the viscosity, you can get the approximate result very well. And condition at the boundary of two medium. So one is something like air and the water, or water and ocean bottoms, for example. And no, this is a boundary. So this is a normal velocity right at the interface point. I'm going to call that V2 in the medium 2, and this is at medium 1, right at the interface point here, normal velocity is the same. That's the one condition. Boundary condition at the boundary. But this is wrong. I put the arrow here. Pressure is a scalar quantity. You can't just put the arrow. I always say it's wrong. I should correct it. I should put the dot here in the medium 2 and dot here at medium 1, saying that that's infinitely close to the boundary. So you should really delete the arrow, but it's, say, pointing the boundary from medium 1 and medium 2. So pressure right at the boundary is the same. So that's what the two condition. So we're gonna deal with. Now reflection of acoustic wave at the rigid boundary here. So usually in high school, you use a ray idea. So ray idea means if this is rigid here, then a ray is coming in, then ray gonna be going out, right? That's what we usually handle that in high school physics. Here, we're gonna really deal with the wave front, okay? So in this case, it's really plane wave for easiness to explain. So this is 90 degree. So wave front is moving in that direction. And also for the reflection wave front is coming out from the boundary. So that's what this line stands for. It's called the incident shock wave front, or simply shock front. And this is a reflection shock front. You got the idea. So this is a rigid surface. The shock wave is coming in any angle, coming straight up here. Then as it hitting it, then reflection wave start from here and coming down this way, right? As it coming up and coming down. So this is the reflection wave. Some nomenclature. It's coming with the alpha angle. And reflection wave is coming out from alpha prime angle. And in high school physics is saying alpha is equal to the alpha prime. You heard, right? Without any question, any reason, the physics teacher said, this is it. Then your answer is yes, that is it, without any question. But that comes from so-called what law? Snell's law. Have you heard about the Snell's law? Snell's. We're going to go through this. Very fundamental, the law which explains alpha is equal to same as alpha. In next page I'm going to show you. So in front of the incident shock wave, I'm going to say P naught, U naught, and C naught is acoustic velocity of the water. Okay? Alpha. Behind this is a P and U. P naught, U naught, and behind here is PU. And after the reflection wave, then behind gonna be P prime and U prime. Right? So our interest is right at this point here, say point O is what our interest to see how the wave react with respect to the rigid wall, okay? And this is a fluid particle velocity. Velocity has direction, so which is a vector. So I put u here, and this normal vector with respect to the rigid surface, this angle is same as alpha, right? Alpha here, alpha here, alpha here. So this normal component is u cosine alpha. Same way. This is alpha prime, and this component is u prime cosine alpha prime. So geometry before we getting into the Snell's law. Snell's law is really sophomore physics. Next, I put the slide which I usually put in the last slide of the section, because as I explained the Snell's law in general, then I can just use the overall situation. In the previous page, this is a rigid. But I said, oh, well, to make it general, explain the whole thing as a one shot, then you can understand the rigid water interface problem and also air-water interface problem. Look at this carefully. It's just very simple and very straightforward. This is the free surface, okay? And this is air. I'm going to say acoustic speed in air is Cg. And acoustic speed in the water is C naught. And the acoustic speed in the water is about 4.5, 4.5 times higher than acoustic speed in the air. So C naught is about 4.5 times Cg, okay? 1,500 meter per second is water, and you divide by 4.5, you can get the air acoustic speed. So here is, I'm going to consider only that portion. So this is incident shock wave moving with this alpha angle, this way. As this is moving this way, so as you look at this wave, as it go up, it's going to come down, right? As it go up, it's going to come down. Make sense? Does make sense? Make sense? So the distance it travel from here to here in the free surface direction is from A point to point B. In normal direction, it's going to be C naught times T. That's the distance, right? And as it comes up, this guy comes down. Total duration of time is time t. So as it comes down this way, it's going to be same C naught times t. No magics here. Now question arises, okay? Question arises. All we know is the C naught we know. Total time t we know. And the speed is concerned, acoustic speed in the water is a C naught. As you consider this point A, as wave is hitting the surface, so this guy will hit it. First will hit. In that direction will eventually finish here. So same time, it will take same time from 0 to time t here. Okay? what's the acoustic speed? Not this direction. This direction is C naught. What about the speed along here? I'm standing here. Watch it. How that acoustic speed is going to move in that direction. Is it higher than C naught? Or equal to C naught? Or lower than C naught? That's my question. That's what the basis of Snell's law. It will take same time T naught, and to look at here, from here to here. I'm going to run from here to here. It will take time T. From here to here, how long does it going to take? Time T, right? So I have to run really faster, much faster than I run from here to here, with the same time T, right? So before the equation, I'm going to let you visualize in your mind what would be the speed. Speed is from here to here. Keep thinking about the particle is hitting along here. That's the question. You catch my question? 여기 I'll talk in Korean a little bit. So here, this is incident shock wave. As it moves with angle alpha, it will hit to the other point, which will take total time t. Of course, the distance from here to here is c naught, speed times t. But as I stand and look at, as the wave goes this way, stand here, along the free surface, I'm going to see the point B. So what's the speed? Same, it takes the same time t from here to here. But as I look at the wave speed should be much faster than C naught. 성태, yes or no? Because I have to run faster. Because distance here, this is longer than this. So what's the speed? 가을학기. Anybody? If you can answer, then I didn't explain right. 봉식, 정호, Abdullah. Is it faster? You think the speed of the wave along the surface, free surface, as I look through, as this wave headed this way, the point along here will hit it, right? Yes, sir. So you see the speed from here to here, speed is faster than C naught, which is the speed from here to here. Distance is longer. You have to move fast, otherwise you will be behind. If it's the same speed as a C naught, maybe you will get about that much distance from here to here. So you have to catch up. You have to really, really run fast. That's natural. So that speed is what the C naught divided by the alpha, sine alpha angle. That's what I'm going to explain. With the understanding visually before the simple equation. Don't look at me like that. Okay, look at this. Look, I spent a whole hour here. That's not good. Let's consider this incident shock wave. Look at here. This is incident shock wave, and moving with the C naught speed is going to bang. It will arrive here, At time t, incident shock wave will arrive here. And reflection wave is concerned at the beginning is here. Then as incident shock wave move, then reflection wave is coming down here. Hanchul, you follow me? Then consider this triangle, right triangle here. The distance AB is equal to, distance C0t is AB distance times sine alpha. Correct? So AB distance is equal to C naught times t divided by sine alpha. Do you see that? So I wrote down here, AB is a distance AB is equal to AC. Okay, this is for reflection wave. BC, this triangle, BC divided by sine alpha. You see that? And now reflection wave, look at this triangle. This is a 90 degree, okay? And the AB is AC prime divided by sine alpha prime. And now transmitted wave, this is air. Transmitted wave, this is 90 degree right here. So AD is AB times sine alpha double prime, which means AB is equal to AD divided by sine alpha double prime. So that's what I wrote here. Simple, very simple. Simple, the equation, sine equation, but that's what the Snell's law is. So here AC prime is C naught times dt, and BC is equal to C naught times t, and CGT, this is a d distance. This is it, right? Then what you can claim here is just move t to down here. And this relation, you don't have to memorize. It's well known, the Snell's law. C naught sine alpha prime, C naught over sine alpha, CG over sine alpha double prime. This is the speed. This is the speed along the surface, free surface, by the incident shock wave. This is due to reflection wave. This is due to transmitted wave. So this is really nothing but speed, wave speed along the free surface right here, free surface. This one page shows nothing but the Snell's law. So from here, these two equations, alpha is equal to alpha prime, and also between the fluid media and this is the air media, you can, that equality, you can rewrite this equality, you can rewrite as sine alpha double prime is equal to CG over C naught times sine alpha. Alpha is given because that's the angle that incident shock wave hit the free surface. Or rigid surface doesn't make any difference. This is Snell's law. Okay? And with that information, alpha is equal to the alpha prime. For the rigid boundary with the water, this is next page, as you see there. C naught sine alpha is equal to C naught sine alpha prime. Alpha is equal to alpha prime. So this is the equation, the shock wave velocity parallel to the boundary. And this u cosine alpha is equal to u prime cosine alpha prime, which is a fluid particle velocity, the normal, which is normal to the boundary. This is for the incident shock wave, normal to the boundary. That's what this is situation. You can say compatibility condition right at the boundary. This plus that, plus and minus, that equal to 0, because this takes place all along here, all along here. We are looking at the point O, so u prime cosine alpha prime has to be equal to u cosine alpha. Right here is rigid boundary point, so sum has to be equal to 0. Okay, my lips is getting a little bit dry, which means desperate to really explain. Okay, with all this information, you can say, well, the alpha is equal to alpha prime. That's what we conformed from here. And u is in the Snell's law. U is equal to u prime from here, which is particle velocity, normal to the boundary. And of course, one assumption is there is no loss in the boundary, okay? Usually right at the boundary or seabed, you know, whenever you face the boundary, there is an energy loss because damping come into picture, things like that. So here, this is incident shock wave situations here. I said P minus P naught is equal to rho naught C naught, U minus U naught for the plane wave. If it's a spherical wave, you have one additional second term, which is one additional term. So for simplicity, I introduced just for plane wave. So when situation arises to deal with a spherical wave, you have to consider one additional term. I think I gave in the exam problems, I don't know when, some years ago maybe, derive all the equation for spherical wave for interface problem. I said u naught is equal to 0. I'm talking about the point O. This section is for the rigid boundary. Rigid boundary, u naught, initial velocity, fluid particle velocity right at the rigid surface is equal to 0. Then u naught has to be equal to 0. So right at the boundary, P minus P naught is equal to rho C u, okay? Naturally. But for the, this part is a reflection wave, right? Reflection wave, of course, you are dealing with front and the rear or back of the reflection wave. That's what you are dealing with. So if you look at that, behind this P prime minus P, so we are really considering around the intersection point right here. Right out here, behind this u prime is coming right out, and u is, I said, is equal to 0, which is right still at the point O in front of the reflection wave. Sometimes it's not that easy. For some people, it's difficult to convince why u is equal to 0. For the reflection wave, behind the reflection wave is u prime, but right in front, I'm talking right at the boundary, right at front, u is equal to 0. When you think about infinitely close to the boundary, before and after, okay? So this point, the term is equal to 0, then you get that equation. So now you can add this guy plus this guy, then you have 2, factor of 2 comes right out there. What does it mean? This 2 is, you can think of as the pressure experienced by the rigid surface, which is twice of the incident shock wave. So what some situation occurs is called, oh, here is another one, which is called the acoustic paradox. Acoustic paradox is, well, what happened? This is rigid. Then I have a shock wave coming exactly normal to the boundary, coming this way, not coming this way. If except exactly 90 degree, this is a wave, this is rigid. Except the 90 degree, when the wave comes in any angle, you can say the pressure experienced by the rigid surface is twice. I explain even using just the physics itself, twice of incident shock wave. But if it's exactly 90 degree, there is no reflection wave. That situation, the rigid surface will experience exactly same pressure as the incident shock wave. Make sense? Don't look at me like that. Right? If it's exactly 90 degree, there is no such a thing as a reflection wave. No reflection wave. So this is a rigid. I have exactly 90 degree wave is coming. There is no reflection. Where the reflection will occur? So any angle except the 90 degree, any angle, if it comes, then there is a reflection wave comes right out there. But the question is acoustic paradox is really a disputing element? Do we have to consider that situations happening sometime? My answer is no. Because physics says the situation that the wave is exactly 90 degree with respect to the boundary, the rigid boundary, but in reality, physical world, there will be no such a situation. Why? Because in real world, exact 90 degree, if the angle is 0.00001 degree, reflection wave will generate. So in general sense, I feel we don't have to worry about the acoustic paradox. We don't have to worry. Always say that the rigid surface will experience the twice of incident shock wave. I think that's really enough, rather than dispute for acoustic paradox. You don't have to really worry about it. That's my claim. This is the free surface. So for the free surface, I explained already when you deal with air, fluid, and the interface problem. This is a transmitting wave, and this is incident shock wave, and this is reflected shock wave. regardless of alpha angle. Alpha is equal to same as alpha prime. As you compute yourself in a minute, as example problem, this alpha double prime angle, very small. Put that in your mind here. When this is very small, means this wave is moving almost straight up. What that means here, when you consider this point as a fluid particle point, and consider that point as approximation as surface ship sitting on there, right here. Surface ship is sitting right here. And what would be the kickoff direction? Almost straight up, because alpha double prime is very small usually, because impedance in the air is very small compared with the water. So Snell's law, as we already look at, for this is with the transmitting the portion here, and all this is really acoustic speed along the free surface, okay? By incident shock wave, by reflection wave, by transmitting wave. Transmitting wave, transmitting, you can use the word refraction. R-E-F-R-A-C-T-I-O-N. That's what another way to call. And this is all coming from relation here. This is coming from relation there. And air-water interface speed ratio is about 4.5. Pretty good, okay? 4.5. And of course, this is the fluid particle velocity normal to the free surface, which means right here, normal. So in water media, if you look at the U cosine alpha, which is 90 degree, upward direction positive. This is a negative direction. U cosine alpha minus U prime cosine alpha prime has to be equal to the right at the intersection point for the air velocity, right here, air particle velocity, which is the UG cosine alpha double prime. Okay, so normal directions like this. So that's what it shows in the next page. Right here. This, okay. Next is, so all three wave here, right at the interface, air-water interface point. Consider first front and back of incident shock wave. Then general equation set is here. P minus P naught is equal to rho naught C naught U minus U naught. So here P naught is equal to rho naught C naught and U naught. Static pressure, then that you can say that cancels up. You have P is equal to rho naught C naught U. For the incident shock wave, for this is reflection wave, front and back of the wave. You can consider this portion I show here. In the same way, you can say in the air media, PG is rho G, CG, and UG. That one equation. And impedance ratio is generally approximately is a 3600 difference, okay? So ratio is 3600, very large. Impedance in air. Impedance in air is 30 rho c divided by 3600. So it's a very, very small. That's the reason, as you will see as example, that's the reason that when you have explosion testing in underwater, I can stand about 50 feet away, about 20 meters away from the actual explosion point. I'm fine. But if I put my feet in the water, then I will have a shock wave hit on my foot. But if I'm to stand away and the pressure escape right from the water, shock wave pressure escape from the water out to outside to air, very small, almost none. So then you don't have too much worry. But still, in the test site, for the safety reason, you have to evacuate about 1 mile. No reason to really move away. But the safety quotient, they still do that, miles away from the test site. Okay, this is a homework. Very important 2 equation, then I'll finish. This is a very important equation. I want you to, this is the first underwater explosion homework due week later, which means Friday next week. And derive this relation using equations 1, 2, 3, and P plus P prime is equal to the PG right at the point O. And I want to derive this equation, and shouldn't be any problem. Okay? So solve this problem, and also verify yourself when using this equation. If you replace air by the rigid surface, you have to make that condition. Impedance of the water is very large compared with the water. Rho C naught. This is water, this is air. So you can use this very good approximation plug in here, and you can confirm the result for the rigid surface water interface problem, which is in over here. I'll explain this Monday briefly. And one example problem I want to go through. And PG is a pressure escape in the air, is a fraction of 1 psi. This is the case for 1,000, P is 1,000 psi, then actually a fraction of the 1 psi escape into the air, which means shock wave almost cannot escape out of the water. So spend some time weekend on this problem and derive the equations. Don't spend more than 2 hours. Should be able to derive in 30 minutes maybe. But if you spend more than 1 hour, something wrong. But you may discuss all the homework. I usually ask students to just to talk together, not copying together, of course, talk together to derive the equations. There are 2 equations that very, very important equations. I'll spend another at least 10 minutes on Monday. Okay, I'll stop right here. Any questions? Okay. All right, so we'll see you on Monday.